Okay, ready to dive into some data structures.
Always.
Today, we're going way past the basics.
Oh, fun. Like what?
We're talking about those data structures that even seasoned programmers might have overlooked.
Yeah, you don't always learn about these in your first couple computer science classes.
Exactly. But they can be crazy useful.
Yeah.
That's why we're calling this deep dive Overlooked Data Structures You Need to Know.
Because you really do need to know them. Once you do, you'll start seeing them everywhere.
I completely agree.
It's like having a secret weapon.
Okay, so we're working from this article, and it basically lays out 7 of these secret weapons, these overlooked data structures, and how they can make your code seriously efficient.
It's a real treasure trove of knowledge. And some of these, once you get them, they're so elegant.
Yeah, you're like, why didn't I think of that?
Exactly.
Okay, so first up, Bloom filters. Have you ever used one of these?
Oh, yeah. They're great for situations where you need to know if something is in a set, but you don't need to be 100% certain.
Okay, so you're saying there's a chance it could be wrong.
There's a small chance of a false positive, yes. But that's the trade-off for incredible space efficiency.
So it's a trade-off, but it's often worth it.
Absolutely. Think of it like this. Imagine you have a massive list of words, and you need to check if a word is spelled correctly.
Okay, like a spell checker.
Exactly. A Bloom filter can quickly tell you if a word is probably spelled correctly.
Probably.
Right, because if it doesn't find the word in its quick check, then you know for sure it's misspelled. No need to check the entire dictionary. Saves a ton of time.
Oh, that's clever. So it's like a quick filter before you do a deeper dive.
Exactly.
Yeah.
And because they're so compact, they're perfect for applications where memory is limited.
I'm starting to see how this could be useful. All right, next up on our list of overlooked data structures is the skip list.
Skip lists. I love these. They're like adding express lanes to a linked list.
Express lanes for data. I like the sound of that. How do they work?
So picture a regular linked list, right? You have to go through each element one by one to find what you're looking for.
Right. It can be slow, especially if you have a lot of data.
Exactly. Now imagine you have another linked list on top of that one, but this one only contains every other element.
So you can skip ahead.
Exactly. And you can even have more layers on top of that, each one skipping even more elements. It's like those mileage signs on the highway that tell you how far it is to the next few exits.
Oh, I see. So instead of checking every exit, you can quickly jump ahead.
You got it. And that's what makes skip lists so fast for searching and inserting data. In some cases, they can even outperform balanced trees.
Wow. They sound super useful, especially for databases and anything where speed is essential.
You got it.
Okay, moving right along. The next overlooked data structure on our list is the trie, also known as the prefix tree.
Ah, tries. They're like dictionaries designed for efficiency.
How so?
Well, imagine you're building an autocomplete feature, like what you see in search engines.
Okay, so as I type, it suggests words I might be looking for.
Exactly. A trie is perfect for this because it stores words based on their prefixes.
Prefixes, I mean, like if I type pre, it would know to show me suggestions like prefix or preview
Yeah.
because they share those first 3 letters.
Exactly. Each node in a trie represents a letter, and the path you take down the trie corresponds to a prefix.
So if I type pre, it follows the P branch, then the R branch, then the E branch, and boom, there are all my suggestions.
Precisely. It's incredibly efficient for searching for words with common prefixes. And it's not just for autocomplete. Tries are used in all sorts of applications, like IP routing and even bioinformatics.
Wow, so it's really versatile too.
It is.
Okay, so we've got Bloom filters, skip lists, tries. What's next?
Let's talk about Fenwick trees. Don't let the name scare you.
Fenwick trees. They sound kind of intimidating, I have to admit.
The name might sound complicated, but they're actually quite elegant once you understand them. They're all about efficiently calculating cumulative frequencies.
Cumulative frequencies. Can you give me an example?
Sure. Imagine you're tracking the scores of players in a tournament. As the tournament progresses, you want to know the total number of points a player has scored so far.
Okay, so it's like a running total.
Exactly. And not just a single running total.
Uh,
You can also use a Fenwick tree to quickly calculate the total score between any 2 points in the tournament.
so if I wanted to know the total points scored between game 5 and game 10, I can use a Fenwick tree to find that quickly.
Exactly. It's all about storing the data in a way that makes those range-based queries lightning fast.
Okay, starting to get it. It's like instead of adding up all those individual scores every time, the Fenwick tree already has those sums pre-calculated.
You got it.
So much faster than brute forcing it every time.
I like it. Okay, so we've covered Bloom filters, skip lists, tries, Fenwick trees. What else is there?
We still got segment trees, disjoint sets, and the Van Emde-Boas tree.
All right, bring them on. Those are some intriguing names, to say the least. They really are. And they solve some pretty interesting problems, too. For example, let's say you're working with a huge data set. Something like, oh, I don't know, maybe stock prices over time.
Lots of data points there.
Exactly. Now, you want to be able to quickly find things like the highest price within a certain date range, or maybe the lowest price over the last month.
Those sound like pretty common queries if you're analyzing stock data.
Right. And a segment tree is built for exactly that kind of thing. It lets you break down that data into segments and then efficiently query those segments to find the information you need.
So instead of looking at every single data point in that range, you can quickly zero in on the relevant information.
Exactly. It's like imagine you have a giant encyclopedia
Okay, I'm picturing it.
and you want to find information about a specific topic. Instead of flipping through every single page, you can use the index to jump to the right volume, then the right chapter, and so on.
Makes sense. So it's all about organizing that data strategically to make those searches super fast.
Precisely. And that's what segment trees do. They organize that data in a way that makes those range-based queries incredibly efficient.
So we've got Bloom filters for probabilistic set membership, skip lists for supercharged linked lists, tries for efficient prefix-based lookups, Fenwick trees for lightning-fast cumulative sums, and now segment trees for powerful range queries. What's next?
Well, we can't forget about disjoint sets.
Yeah.
Imagine you're building a social network and you need to keep track of who's friends with whom.
Okay, so like, is this person in the same friend group as this other person?
Exactly. Disjoint sets let you do that really efficiently.
Yeah.
You basically start with everyone in their own separate group, and then you can merge those groups together as people become friends.
So it's like, initially, everyone is an island, and then as they make connections, those islands start to merge together into larger land masses.
I like that analogy. And the cool part is, disjoint sets have this really elegant way of keeping track of all those mergers. You can instantly check if any two people are in the same friend group, no matter how many times those groups have been combined.
It sounds like it could get pretty complex with millions of users all making friends and maybe unfriending each other.
It can. But disjoint sets are surprisingly efficient. Even with those huge, constantly changing networks, they're used in all sorts of algorithms, like Kruskal's algorithm, which we might have time to get into later.
Ooh, a teaser. Okay, now I'm even more curious. But first, we've still got one more data structure on our list, the Van Emde-Boas tree.
Ah, yes. The Van Emde-Boas tree, the final boss of overlooked data structures.
It sounds pretty intimidating.
Maybe a little, but it's also incredibly powerful. Think about it this way. Remember how a skip list is like adding express lanes to a linked list?
Yeah, I remember those express lanes for data, speeding things up.
Right, so imagine taking that idea of adding layers and applying it to a search tree.
Layers on top of layers. Getting a bit meta here.
That's a good way to put it. The Van Emde-Boas tree takes that multi-layered approach and uses it to create a structure that's insanely fast for certain types of operations, especially if you're working with integers within a specific range.
Okay, so if I'm hearing you correctly, the Van Emde-Boas tree is like a supercharged search tree, optimized for speed when dealing with those integer keys.
You got it. It's not something you'd use every day, but when you need it, you really need it. Think high-performance databases, specialized algorithms, situations where speed is absolutely critical.
So it's kind of like the Formula One race car of data structure.
Exactly. Not the most practical for everyday driving, but when you need to squeeze every ounce of performance out of your code, the Van Emde-Boas tree is there to blow you away.
I love that we're ending on the final boss of overlooked data structures. It feels appropriate.
It does, doesn't it? But honestly, I would even call them overlooked at this point, not after this deep dive.
You're right about that. I feel much more familiar with them now.
Me too.
Okay, so we've covered a lot of ground here. We've talked about Bloom filters, skip lists, tries, Fenwick trees, segment trees, disjoint sets, even the mighty Van Emde-Boas tree. It's been quite a journey through the world of data structures.
It really has. And these are just a few of the overlooked ones. There are so many more out there, each with its own unique strengths and weaknesses ready to be explored.
You've definitely sparked my curiosity. Now I kind of want to go down the rabbit hole of all the lesser-known data structures and see what hidden gems are out there. Maybe that's a deep dive for another time. But for now, I think we've given our listeners plenty to think about.
I agree.
So many fascinating structures, and they all have such cool names. Bloom filters, skip lists, tries, Fenwick trees, segment trees, disjoint sets, Van Emde Boas trees.
Right. They sound like something out of a fantasy novel.
They really do. Okay, so we've covered a lot of ground here. We talked about how each of these data structures solves a specific type of problem, and we even touched on some real-world scenarios where you might use them. But if you had to boil it all down, what's the key takeaway for our listeners?
I think the biggest thing is to just be aware that these structures exist. You don't need to memorize every detail about how they work, but just knowing their names and the types of problems they solve can be incredibly valuable.
Yeah. It's like having a mental toolbox. You might not use every tool every day, but when you come across a problem that requires a specific solution, you'll know exactly which tool to reach for.
Exactly. And sometimes just knowing that a particular tool exists can spark a new way of thinking about a problem.
It's like, oh, I could use a try for this instead of trying to reinvent the wheel.
Exactly. And the more tools you have in your toolbox, the more creative and efficient you can be as a programmer.
I completely agree. It's all about expanding your horizons and exploring new possibilities.
Absolutely. So next time you're facing a coding challenge, don't be afraid to get creative. Think about these overlooked data structures. Think about the specific problem you're trying to solve.
Yeah.
And who knows, you might just discover the perfect tool for the job.
I love that. Well said. And on that note, I think we'll wrap up this deep dive.
Until next time.
To all our listeners out there, keep exploring, keep experimenting, and keep coding.